quite hard, 9 differential equations, subject to 6 constraints. Any question?
For the second part where the matrices are multiplying each other, there's a negative sign in front of the.
Negative, yes.
Yeah. So when you calculate that, did you already take account of it?
Yeah. So negative times negative is positive negative. This is the positive negative. Jeff, says what? Oh yeah. Any question? I mean, you will be tested or not tested, at least in the home, on this. Any question? Okay, let's move to the maybe more practical and more interesting part, which is Euler angles. Next time we will make a table like this, showing different ways of representing rigid body attitude. Or, obviously, the straightforward way is to represent it using the rotation matrix. The second way is using Euler angles. What is the premise? What is the principle here? The principle is that which Euler said is that the attitude of any rigid body, you're here representing it by 9 angles. This is straightforward, brute force, but it's not an efficient way of doing it. Because 9 angles subject to 6 constraints, you should be able to solve this set first and reduce it to 3, right? Of 9 variables, but there are 6 relations amongst them. So you should be able to eliminate 6 and get rid of these 6 extra and just reduce it to 3 independent, right? And that's what he proposed. He said, well, the attitude of a rigid body is is ultimately represented by 3 rotations, just 3 rotations. Any given attitude, give me any attitude. So you do whatever, this attitude of the rigid body with respect to some inertial fixed axis. Well, I can represent this frame with respect to that frame by just 3 axes. 3 rotations, I'm sorry. 3 rotations about 3 different axes. So the attitude of a rigid body, any arbitrary given attitude of a rigid body is represented by 3 rotations, successive rotations. 3 successive rotations about 3 different axes. And it's up to you to select how to rotate. We're going to talk about that. So, this is a rigid body. Again, the x-axis, like I'll use the convention for an airplane. The x-axis is the longitudinal axis towards you. The y-axis is starboard to the right. And the z-axis completes the trap, it's downward. Okay? So, well, here is an attitude of a rigid body. It's simply I did yaw, okay, by 90 degrees. So this is an attitude. And I want to represent this attitude with respect to the inertially fixed attitude, the initial one. Well, one representation is simply by a single rotation, 90 degrees about the z-axis, okay? But you can do it in a totally different way. I can do it the following way. Roll 90 degrees, pitch 90 degrees, roll back negative 90 degrees. The end result is the exact same attitude, okay? So, given any general attitude, I can always represent it by 3 successive rotations about 3 different axes. So for example, I can choose to rotate first about the z-axis, z inertia. I'll get a new frame. Then I will have the next rotation has to be about a different axis. It cannot be about the same z-axis. Okay? So say I will rotate about y, the new one. Now I'm going to do the third rotation. I cannot rotate about y now, because like I said, it has to be 3 different axes, not the original z, not the most recent y, pick up any other thing. So maybe the most recent x. These are 3 rotations. Using these 3 angles, theta 1, theta 2, theta 3, you can completely characterize the rigid body attitude, which means you can completely write the rotation matrix R in terms of these three angles, theta 1, theta 2, theta 3. You can do it the other way around. Z, instead of rotating about Y here, I'm going to rotate about X. Right? And let's do it this way. ZY, there's nobody preventing me from rotating about the new Z. Old Z, new Y, new Z. Okay? They are different. And I can do the same with X. ZXY or ZXZ. This Z is the very original Z, is the inertial Z. But this Z is the most recent one. I'm always rotating about the most recent one. Here I rotate about Z. I got a new frame. In that frame I have a new x-axis, I'm rotating about it. I got a second new frame. In that frame I have a new y-axis, I'm rotating about it, and so on. Okay?
So the first frame is the body frame or the inertial frame? The first rotation.
Inertial frame,
Inertial
you
frame.
get the first intermediate frame, it's fictitious. Second intermediate frame, then the body frame after the third rotation. We're going to talk about it in detail. And before that, doing that, this is how many combinations? This is 4 combinations, right? This all 4 combinations starting with Z, but I can do it starting with Y or starting with X. So I'm multiplying this by 3. So the result is 12 possible combinations. Okay? You can do it using one of these 12 ways. The most common way, is the ZYX. And you know we like to keep track of the numbers of axes. So Z is always 3, right? 2, 1. We call it the 3, 2, 1 rotation of Euler angles. And we name the angles, this is the standard notation. The angles are psi, theta, phi. This is 12 possible combinations. Okay, look at this. So I have the inertial frame, the N frame. Okay? I'm going to rotate from the N frame to a new frame, intermediate frame. It's a fictitious frame. You don't see it. Some frame. Let's call it the E frame, for example. How you go from here to there? This is the first rotation. It's about the z-axis or the third axis by an angle called the psi. So I'm going to rotate by psi about the N3 axis. Okay? Then from E frame to another fictitious frame, let's call it S frame. We decided that we're going to pursue this, the most common notation. You can do any of these. But let's do the most common one. The 3, 2, 1, or the ZYX, or the yaw H roll. So we're doing this now. I'm doing the second rotation, which is a rotation by an angle theta about the second axis, or the y-axis. The second axis is the E2 axis. Okay? Please keep track. This is very important. And finally, the third rotation. Euler hypothesized that you can describe the attitude of any body. So finally, the goal is to arrive at the body frame starting from the inertial frame. He said you can do that using 3 successive rotations. I did the first, the second, and I'm doing now the third and the final one. So luckily I arrived at the body axis according to Euler. This final rotation, I chose it to be an angle named phi about the first axis, S1. Any question about that? So we're going to do these 3 rotations to write down the rotation matrix, the intrinsic description of the rigid body attitude is the rotation matrix. You're claiming that you're gonna just need 3 angles, which means that the 9 components of the rotation matrix can be written in terms of 3 angles only. You need to show that. Second, and more importantly, is that, well, how your kinematic differential equation would look like. I don't want to use 9 differential equations anymore. You're claiming 3 angles. I want to know how these 3 angles will evolve given omega. Okay? Yes, please.
According to this, we cannot do rotation about third axis twice. Is that true? So
See?
we are doing third axis, then we are doing second.
2 here. I can do S3 for sure because S3 is not the same as N3. I cannot do N3 again. That's right. So once you do N3, you cannot do it anymore. Once you do E2, you cannot do it anymore. Here I can do the third axis again, which is S3. So this is why we have ZYZ. This is 3, 2, 3, right? Yeah, this is one of the legitimate ways of doing it. Any question? Yes, Kevin?
Is S2 equal to E2?
It's very good. This is very good. I'm rotating about N3, so it remains constant, right? So in the new frame, the third axis is equal to this guy, right? Here I'm rotating about E2, so the second axis remains constant. So this is S2, right? And this is what?
B1.
This is what?
B1.
B1. Any question about that? Any question, please? Okay, let's do it one at a time. One at a time is very easy. You're doing a single rotation in a plane. This is very easy. I have here N1, N2, and N3 is out of the board, right? I'm doing a single rotation about N3 by an angle psi. This is pretty straightforward. So here is my positive rotation about N3 by an angle psi. So this guy became, we call it E1, and this guy became E2, right? Any question about that? And what is E3? Yeah. Okay. Let's relate the E frame to the old inertial frame. I want to write E1 equals E2 equals E3 equals, right? This is the goal. In terms of N1, N2, N3. Okay? The third law is very easy.
0, 0.
The third equation is what? E3 equals what?
0, 0,
N3, which is 0, 0. Okay, very good. The first equation for E1, here is E1, it's cosine psi N1, and sine psi N2, and 0 in the N3. E2 is cosine psi N2, but negative sine psi in the N1 there. Okay? This was a very simple and straightforward rotation because it's only single rotation in the plane. It's easy to do. Any question about this? Anybody cannot construct a rotation matrix like this? Cannot derive it like I did now. Any question? There's a question here? No? So I will call this rotation. This is a rotation matrix, right? Yeah, I will call this rotation matrix. By an angle psi, I'll give it a subscript like this. By an angle psi, about the third axis. Okay? So why didn't you call it about the N3 axis? Because it doesn't matter. If you are rotating about the third axis, whether it's N3, whether it's E3, whether it's S3, whether it's B3, it will be the exact same picture. So this rotation matrix, I don't care about where are you going from to. As long as you're rotating about the third axis, here is the rotation matrix. So the rotation matrix by any angle alpha about any third axis will always look like this. 0, 0, 1, 0, 0, 1, cosine the angle, sine the angle, negative sine the angle, cosine the angle. This will always be the case. And I want you to get it first hand like this. Okay? Any question about that? So actually, it's not only the third axis. If you want to do r by an angle, say beta, about the first axis, I can construct it first hand. I will not derive it anymore. I derived it once, and I know its construction. It's very easy. I'll get first hand. And I don't care about what first axis that is. It's the first axis of any frame. Well, the third axis was 0, 0, 1 and 0, 0, 1 in the 3, 3. Here it will be about the 1 and 1.
1, 0,
1, 0, 0, 1, 0, 0, and you'll take the exact same block and put it right here. Cosine, sine, negative, sine, cosine. Cosine the angle, sine the angle, negative, sine the angle, cosine the angle. Okay? And I want you to know how to do it first hand. I mean, in final, whatever, I will not take into account the time that you will take to derive it. I will assume that you can do it first hand. So likewise, I can also do any rotation matrix, by an angle, say gamma, any angle about the second axis, right? Now you have this one is in the 2, 2 element. Okay? Any question about that? And you're gonna put your block cosine, sine, negative, sine, cosine. Cosine the angle. But, like anything, the second dimension is always cursed. You do the determinant, you do this guy, so there is a minus sign here. Only in the second, okay? Only in the second you switch. A little bit confusing, you need to remember. Okay? Okay, so actually we're done. I have the 3 rotation matrix, matrices first hand. I can do it straight away. Yeah, this is hard. I need this, and I need that. There's a question, please.
Is it cosine?
Yes.